Hey everyone, and welcome to this explainer. I am absolutely pumped to have you here today because we're tackling a topic that's kind of a rite of passage in data structures and algorithms. We are diving into the great debate, recursion versus iteration. If you write code, you've definitely faced this crossroads. Today we're going to break down exactly how these two approaches work, uncover some hidden trade-offs, and basically arm you with the knowledge to make the right call every single time you sit down to write a function. Let's get right into it.
Okay, let's dive into Section 1, the danger of recursion. It's not always as elegant as it seems.
I really want you to let that statement sink in for a second. You know, recursion gets this massive amount of hype in the dev community for being beautiful. It's constantly praised as this super elegant, almost mathematical way to write code. But here's the honest truth. Recursion is not always elegant. Actually, if you aren't careful, it is literally just a stack overflow waiting to happen, meaning your program just completely runs out of memory trying to remember where it came from. That dreaded program crash? That's the dark side of elegant code, and it frames the exact central conflict we're exploring today.
Moving on to Section 2, defining the contenders, establishing the ground rules.
Right, so before we can crown a winner for your specific problem, we really need to define our contenders clearly. First up in the ring, we've got recursion. By definition, a recursive method is one where a function calls itself from within its own code. And what makes it feel so clean, magical really, is that it uses the system's call stack to handle the state for you, completely automatically. You don't have to sit there manually tracking every single little variable change. The system stack is doing all that heavy lifting behind the scenes as it dives deeper and deeper into those function calls.
Now, contrast that with iteration. Iteration is a method that uses your standard run-of-the-mill loops to execute a block of code over and over again. There is absolutely no self-calling magic here. It's straightforward, it's highly hands-on, and it relies on those exact looping constructs you probably learned on day one of programming. With iteration, you're the one in the driver's seat, manually managing the state, the counters, the conditions, the whole shebang.
Section 3, choosing your approach. Let's look at where each method thrives.
And this brilliantly illustrates the divide between the two. Recursion is it's so much cleaner when you're dealing with complex data structures like trees and graphs. It is the undisputed perfect fit for divide-and-conquer algorithms and backtracking problems, specifically because that implicit call stack tracks your position so flawlessly. But contrast that with iteration, which is the heavyweight champion for performance-critical code. If your problem involves incredibly deep inputs, where we risk that nasty stack overflow we talked about, or if the state is just simple to track, iteration is absolutely going to give you that raw, reliable performance power.
Section 4, under the hood, memory and the hidden complexities of the call stack.
Okay, to really understand why iteration sometimes wipes the floor with recursion on performance, we have to look under the hood at implicit stack space complexity. See, recursion inherently uses O of depth stack space. So if you're traversing a beautifully balanced tree, your space complexity is O of log n. The risk level there, delightfully low. But what happens if you hit a skewed tree? Suddenly, boom, your space complexity shoots all the way up to O of n. Your recursion goes exactly as deep as the number of nodes, and sitting right there at that high-risk level is our old enemy, the dreaded stack overflow.
But wait, let's talk about a potential performance savior, tail recursion. This is a very specific scenario where the recursive call is the absolute last operation performed in a function. Why is that such a big deal? Well, because when there's nothing left to compute after that recursive call, some programming languages are actually smart enough to optimize it behind the scenes directly into iteration. You get that gorgeous, clean syntax of recursion, but with the rock-solid memory safety of iteration. It's basically the best of both worlds.
Now, what's really interesting about this point is, well, it might be a bit of a heartbreak if you're a Java developer. Because here's the major gotcha. Java does not optimize tail recursion. No way. No matter how flawlessly you write that tail recursive function, the Java compiler is not going to step in and save you from piling frames onto the call stack. So you absolutely must stay vigilant about your stack depth if you're operating in that environment.
Section 5, the interview strategy, navigating the technical interview.
Let's bring all of this theory back to your immediate reality. How do you handle these trade-offs when you're sitting in a high-pressure interview? So the crucial point is this. Every single recursive solution has an iterative equivalent that uses an explicit stack. And let me tell you, interviewers absolutely love to test this. They'll hand you a classic example question. Maybe they'll ask you to write a depth-first search for a binary tree, or to compute the nth number in the Fibonacci sequence. You'll write this beautiful recursive solution. The interviewer will smile, and then they'll hit you with, great, now convert it to an iterative solution.
They want to see if you really understand how to manually build that stack the system was previously managing for you.
So, to make sure your technical interview game plan is rock solid, lock in these 3 quick takeaways. First, default to recursion for code clarity. It proves you can write clean, elegant, readable code. Second, deeply understand that explicit stack conversion. You really need to know how the machine tracks memory. And third, always be ready to rewrite your DFS or your Fibonacci solution iteratively the second the interviewer asks for better performance or memory safety. I want to leave you with this final, somewhat provocative thought. You know the trade-offs now. You know to default to recursion for clarity. But are you truly prepared to manually build an explicit stack when the interviewer suddenly demands an iterative conversion? That right there is the ultimate test of your mastery of data structures and algorithms. Don't let the call stack hide its secrets from you. Dig in, practice the manual conversion, and be ready for whatever the problem or the interviewer throws your way. Thanks so much for joining me for this explainer. Keep building, keep learning, and I'll catch you next time.